Well, good day, everyone, and thank you for joining us today. My name is Dave Mercer, and I will be the moderator for our presentation. I'm a member of Fluor's Office of Technology, which focuses on using science and innovative engineering technology to build a better world. Our engineers, designers, and experts, that is our people, are at the core of our success. Today's webinar is titled Hydraulic Surge, From Screening to Detailed Modeling. In our industry, we continuously strive to improve the safety and operability of the plants that we design. One phenomenon that is receiving increased attention is hydraulic surge. Hydraulic surge, often referred to as water hammer, can have devastating results, potentially leading to asset damage, serious injuries, or even the loss of life. Today's webinar will walk you through the complete engineering life cycle associated with hydraulic surge, from early screening activities to the identification of potential problem areas and detailed simulations and surge countermeasures. Now, to set the stage for today's webinar, with the HSE topic, please join me in welcoming Niels Siesner. Niels, now over to you.
Thanks, David, for the introduction. And it's my pleasure to present the safety topic today. For my part in today's webinar, I have selected to cover two incidents that demonstrate how destructive hydraulic surge can be. I want to mention that for like many incidents, the events were the result of several independent factors, which together eventually resulted in the surge incidents. The first incident that I will highlight is one of the earliest well-documented surge incidents and takes us back to 1950 in Japan, at the Oigawa hydroelectric installation. As is demonstrated on the slide, the Oigawa facility is a power plant that contains three identical hydroelectric turbines that convert the energy of flowing water into electricity. Next to these three main turbines, the facility also contains two smaller turbines, one for generating power needed by the power plant itself, and one coupled to a standby oil pump, which played an important role in the incident that occurred. On June 18, in 1950, the Oigawa facility underwent routine maintenance to clear out sand that has built up over time in penstock 1. This meant that during the maintenance, penstock 1 would be isolated and drained. It should be noted that both the house turbine and the oil pump turbine were connected to penstock 1 at the time of maintenance and would therefore not receive any water. During the maintenance activities on penstock 1, it was decided to run turbines 2 and 3 on no-load operation, meaning that they would not be generating any electricity, a decision made due to a lack of operator availability. As no power was generated within the facility, this put a significant strain on the external power supply. As a result, voltage dropped and undervoltage relays in the power plant were tripped, which shut down the oil pumps. The backup oil pump turbine, designed to take over in such a scenario, was connected to penstock 1 and remained idle. As a result of losing the oil pumps, oil pressure decreased rapidly. The oil system at the power plant was used for controlling the wicket gates, controlling the water flow to the turbines, and the turbine bypass pressure regulators. Without any oil pressure, this meant the flows through penstock 2 and 3 rapidly increased as the wicket gates and pressure regulators moved into their hydraulically balanced, more open positions. As the flow of water in penstock 3 increased to velocities of about 4 meters per second, the butterfly valve, which was in a slightly closed position, slammed shut. Hydraulic surge was a known phenomenon even in the 1950s. And the butterfly valves installed in the penstocks were intentionally designed to have a closing time of no less than 28 seconds to prevent hydraulic surges. Unfortunately, as its oil cylinder was empty, it instead closed nearly instantaneously. A pressure peak of roughly 42 bar resulted, which critically ruptured the penstock 3. As a result of the rupture, excessive water discharge resulted in a vacuum higher up in the penstock, which in turn led to large upstream sections collapsing. During the incident at the Oigawa power station, 3 operators tragically lost their life. The second incident that I want to highlight happened in 2016 in an alumina refinery in Jamaica. Production of aluminum at this facility is done using the Bayer process. The first step of the Bayer process is called the digestion step. In this step, hydrated oxide is dissolved from bauxite in a sodium hydroxide solution at elevated pressure and temperatures. The resulting caustic slurry is then flashed and reduced in pressure and temperature in a series of vessels before being discharged to a clarification step for further processing. The surge incident I am highlighting today took place at the pumps discharging the slurry from the final flash vessel, which is a vessel operating at roughly atmospheric pressure and 110 degrees Celsius. The surge event occurred during a routine procedure, which involved a manual switchover from the main operating pump to a nearby parallel pump. As per operating procedures, the parallel pump was started against a closed discharge valve, an angle valve in this case, with the main pump still in operation. After this, the main pump was shut down. At this exact moment, the valve spindle of the angle valve installed at the parallel pump ruptured, as can be seen on picture B in the slide. As a result of the spindle rupture, the disc on the discharge valve could now move freely, and the pressure and flow from the pump caused the valve disc to slam into the closed position. This sent a high-pressure water hammer wave back towards the pump. The pressure peak was estimated being as high as 140 bar at the valve, which was located only 7 meters away from the pump, and roughly 100 bar at the pump itself. The pump casing was designed for roughly 7 bar gauge. During the event, the pump casing failed catastrophically, as shown on the picture in the left. This resulted in spraying hot caustic in the area and seriously injuring the nearby operator. I hope these safety topics have provided some insight on the destructive forces that can occur due to hydraulic surge, and why this phenomena deserves our attention during project development. With this, I conclude my HSE topic. I will now hand the word over to Thomas, who will explain in more detail how exactly these forces are being generated and how we can identify these risks on our projects.
Thank you, Niels, for that very relevant safety topic, illustrating the drastic effects that this phenomenon can have if left unconsidered. To gain a better understanding of all aspects of surge across the board, we've put together today's webinar. I will begin with the basics of surge, a physical description of the process. I'll then touch upon surge screening as a part of project execution, and will end with the features and limitations of surge screening. After this, I'll hand over to my colleague, Liang, who will take you through the aspects of a detailed surge simulation, including how it differs from screening, what you can expect to encounter in a model, and what options one has to mitigate the effects of surge once a problem has been identified. But let's start at the beginning. Did you know that modern industrial complexes or refineries can contain upwards of 10,000 pipelines? That means that the total length of piping within these complexes can be in the range of hundreds of kilometers. Importantly, each of these pipes needs to be subjected to rigorous checks so as not to be a hazard during operation. During the early phases of a project, one often finds that neither the information on each of these lines nor the time to check each and every one of them is available. This is where screening techniques come into play. They offer a convenient method to quickly identify or screen out problem areas, which can then be investigated in detail later using all the advanced techniques and with the precise knowledge available in later phases of a project. Screening techniques find their origin in simplifying assumptions made to solve the governing equations of hydraulics. Of course, this makes it necessary to be able to describe the phenomenon of surge. So what is it exactly? Put simply, hydraulic surge is a pressure shock wave that occurs when the kinetic energy of a fluid is converted to potential energy in the form of pressure upon a change in velocity. This wave travels outward from the effective source of the velocity change through the fluid at the speed of sound within that fluid. As a physical phenomenon, hydraulic surge adheres to our fundamental conservation laws. Imagine a section of pipe located somewhere between a high-pressure source and a valve. This section is traveling with a shockwave that has been created by stopping a fluid moving within by closing the valve. We can assert that the mass entering the section is equal to the mass leaving it. However, because this is a shockwave, it is important to note that the fluid does not conform to our usual assumption of incompressibility. Additionally, we can state that the force acting on the fluid due to the pressure at the boundaries of our pipe section must be equal to the net momentum flux into that section. From this, the equation on the right-hand side of your screen can be derived, which is usually truncated due to the very small effect of initial velocity relative to the sonic velocity in a liquid line to create the well-known Joukowsky equation. Gases, of course, suffer less from surge due to their compressible nature dissipating any abrupt changes. In this equation, we are left with the parameter c, the sonic velocity of the fluid. This is a parameter of major importance when calculating the pressure spike. It is primarily a function of the fluid itself, taking into account its density and bulk modulus, but also varies with properties of the pipe, such as its diameter, wall thickness, and material characteristics, and even how the pipe is supported. This all sounds rather abstract, so let's illustrate it by means of an example. Consider again our pipes with a high-pressure source at the upstream end and a valve downstream. The pressure profile along this pipe may look something like this. On the other end of the pipe, the valve could have a characteristic curve that changes over time, like this. Let us consider the pressure profile at the downstream end of the pipe. You will notice that immediately upon closing the valve, the kinetic energy of the fluid is converted into pressure energy. This shockwave is transmitted through the pipe and reflected at the end of the line, now traveling back to the source and compressing the fluid at the upstream end. At this moment, an interesting phenomenon occurs. The pressure is highest at the valve and lowest upstream, exactly opposite to how we started. This allows the fluid to relax, releasing the stored potential energy, which causes a low pressure wave to propagate through the fluid. Once this low pressure wave reflects from the upstream end of the pipe and returns, the process is restarted and continues until eventually the frictional losses have dampened out the pressure waves. Something important to note is that in this case, the time it took for the wave to travel to the upstream end of the pipe and return to the valve, known as the pipeline period, was exactly the time it took to close the valve. Hence, our assumption of a velocity of 0 at the outflow of our pipe section was true, and the Joukowsky pressure is expected. This is also the case. Interestingly, the value of the low pressure wave can also be estimated as the negative Joukowsky pressure if one ignores losses due to friction. This is potentially important as, if the pressure in the fluid drops to the vapor pressure of the liquid, cavitation, or the partial vaporization of the fluid in the pipe can occur. In the worst case, this can lead to the liquid separating within the pipe, with a vapor space created in between, known as column separation. Sudden collapse of this large volume of vapor can cause significant velocities in the liquid, with subsequent pressure waves ensuing. But what happens when we change the closing time of the downstream valve to be longer than the pipeline period, as in this case? Suddenly, the liquid, pressurized by the returning shockwave, can expand and initiate the propagation of the low pressure wave before all the kinetic energy of the fluid can be converted, as the wave has returned before the valve is finished closing. The conversion of kinetic energy is superimposed on the propagation of the low pressure wave and results in both a lower positive pressure as well as a lesser negative pressure than the Joukowsky equation would suggest. Many attempts at accounting for this reduction have been made, and Fluor has its own in-house engineering and analytical methods on how this is done best. Note also that this reduction in surge pressure is exactly the same effect as would be achieved by closing the valve in a slower manner, in a line that had previously exhibited the Joukowsky pressure. The correlation can therefore also be used to create preliminary estimations as to the reduction of surge pressures due to the mitigating effect of longer valve closure times. And what does all this have to do with surge screening? I mentioned earlier the unbelievable number of pipelines contained in a modern refinery, industrial complex, or power station. Not all of these pipes are created equal. Different pipelines have different physical characteristics. They transport different substances, and they operate at different conditions. Engineering codes serve as a guideline for the design of these piping systems. EN 13480-3, applicable to metallic pipes, stresses the importance of performing surge analyses to account for dynamic pressure fluctuations, but remains vague on how this is to be done or how much overpressure is allowed. ASME B31.3, applicable to pipes within process units, allows for an overpressure of 33% during transient events. And ASME B31.4, applicable to long overland or offshore pipelines, allows for up to 10% overpressure during transient events. Knowing when which code is applicable is of critical importance to the correct implementation of a project and is something that our flow assurance group has a large amount of experience in. And despite today's amazing computing capabilities, it is not feasible to create detailed models of all lines and for all upset cases. Therefore, simplified models of the hydraulics of surge are still necessary to determine or screen out areas that are deemed to be at risk. These models rely on the Joukowsky equation or variations thereof, as has been illustrated here. These areas can then be subjected to further detailed analyses with mitigating measures developed. So, this leads me to a summary on screening for surge effects. Surge screening allows us to quickly estimate the maximum pressure increase and maximum pressure drop in a line due to change in fluid velocity. This allows us to quickly identify parts of a system that need to be modeled in detail. Modifying the Joukowsky equation allows us to make it generally applicable to most real systems and even lets us use the equation to predict the mitigating effects of a slower valve closure. Of course, this approach does have its limitations. It is limited to single-line, single-event cases. Often, closing a valve in one location is accompanied by a change in process conditions somewhere else. Additionally, it assumes constant fluid and system properties. For most systems, the fluid properties do not change quickly enough for a hydraulic surge to be affected. However, it is important to realize that this is not necessarily the case. Screening methods can also not account for interactions between events where superimposing reflected pressure waves may result in even greater pressures. Finally, screening does not consider pressure increases due to secondary effects, such as column separation, the recovery of frictional pressure drop in long lines, or the effect of pipeline fittings. These can, of course, be accounted for in detailed models of the system, as my colleague Liang will now illustrate.
Hi everyone. I'd like to express my thanks to Thomas for his insightful presentation on the fundamentals of surge analysis. So now let's go slightly deeper into the detailed hydraulic transient simulations. In this section, we will explore the purpose of these simulations, when they are necessary, why they are crucial for comprehensive understanding of surge events, and how detailed simulation can be carried out. So the first question to answer is, when do we need detailed analysis? What we show here is a typical project lifecycle chart, including different project phases. Typically, we aim to conduct detailed simulations as early as possible in the project lifecycle. This allowed us to identify potential surge issues early on, enabling timely design modification and mitigation strategies. While some data may not be available at the outset, we can often estimate these parameters based on engineering experience and relevant references. The specific phase at which detailed simulations are conducted can vary depending on the project type. For example, in typical process plant projects, they are often carried out during the detailed engineering phase, when most data is available. However, for pipeline projects, they are often performed during the conceptual or front-end engineering design phase to facilitate early identification and mitigation of surge risks. Detailed simulation can also serve the purpose of incident investigation, followed by surge events or verification of plant modification during startups or maintenance phases. Since we discussed when, now we need to answer why do we need detailed simulation? So why surge screening tool can help identify potential surge issues in process piping systems. There are certain scenarios where detailed simulations are essential. Complex hydraulic network. When analyzing hydraulic network, the detailed simulations are necessary to accurately capture the dynamic behavior of the system. Especially network systems with piping connections of different pressure ratings are required to have transient analysis carried out in order to check the risk of overpressure at spec break boundaries. The one extreme scenario is the verification of HIPs. The complex fluid. For complex fluid like multi-phase fluid or non-Newtonian fluids, detailed simulations are required to account for the varying properties of this fluid under different conditions. If the viscosity and density of a fluid change significantly with pressure and temperature, detailed simulation can help predict the impact of these changes on system behavior. The hydraulic components and variable boundaries. The presence of hydraulic components like pumps, variable level reservoirs, or heat exchangers can introduce complexities that necessitate the detailed simulation. The surge condition consider high and low pressure under max and minimum flow situations that will not be possible to be evaluated by any other means. Then active control philosophies. When complex flow and pressure control strategies are in place, detailed simulations are crucial to evaluate the effectiveness of these controls in mitigating surge. Please note that surge analysis is the only way to consider cascade event of system that relies on pressure regulators or control valves. Column separation. For severe surge events involve column separation, vapor cavity formation, and subsequent cavity collapse. Detailed simulation can provide insight into the magnitude and duration of these events while evaluating the worst-case surge pressures associated with this type of event. It is advised that liquid systems with elevation difference more than 13 meters often need to consider a more detailed transient model that will review the behavior related to those phenomena. Surge mitigation designs. When designing detailed surge mitigation solutions beyond only manipulating the valve closure time, such as adding bypass lines, installing L valves, or sizing surge accumulators, detailed simulations are essential to assess the effectiveness of these measures. The surge analysis could provide dynamic loading on elbows and straight sections that is required in piping stress analysis and support design. In this slide, I'll briefly touch the detailed simulation methodology, including the governing equations and their numerical solutions. The fundamental equations that govern hydraulic transient in liquid pipeline system are derived from the conservation of mass and Newton's second law of motion, as mentioned by Thomas earlier. By applying these principles to a small control volume within the pipeline, we obtain a set of non-linear partial differential equations. And these equations, the continuity equation and the momentum equation, are challenging to solve analytically due to the non-linear friction term. To solve these equations, two widely used and accepted numerical solutions are the Lagrangian wave characteristic method, WCM, and the Eulerian method of characteristics, MOC. The prime distinction between these two methods lies in how pressure waves are tracked within the pipeline. While MOC tracks disturbance on a fixed grid, the WCM follows the propagation of wave directly. Of the two, the MOC method is the most popular technique for solving transient flow equations, and this is the foundation of many modern commercial computational software packages. For some other softwares, for example, SPS use a weak form solution, which is similar to affinity volume method. Lots of people get confused between surge and pressure transient. Under some situation, those two terms are interchangeable, especially under single-phase analysis, for example, water lines, where water hammer is more familiar by most people. In multi-phase fluid, surge issue is often less severe due to the presence of gas phase. In this case, the definition of surge analysis is often related to slug or churning flow conditions in which the momentum change or slugging force is a major concern. In multi-phase analysis, hydraulic transient is more often related to ramp up, ramp down, start up, shut down, cool down, rather than valve closure or pump trips. Hence, hydraulic transient is often part of a larger scope of work, namely flow insurance study, which is not our topic of today's presentation. And in today's presentation, I will try to focus our topic on single-phase surge analysis only. However, while multi-phase fluid are less prone to severe pressure surge compared to the single-phase fluid, there are specific scenarios where multi-phase transient are still necessary. For example, when considering the fluid structure interaction, the steam hammer events such as geothermal plant, the multi-phase loading or unloading lines where the quick decoupling is foreseeable. And in this slide, I'll briefly discuss some popular commercial software tools used for hydraulic transient simulations. Please note that while these tools are powerful, they are not fully automated. They require careful input data and informed interpretation of the results. Remember, a simulation is a prediction based on the provided inputs. Hence, the quality of the output depends on the quality of input data and scenario selection. So please find a list of typical single-phase and multi-phase transient simulation tools, of which Fluor currently have license of roughly half of them. And please note that a different software has its own pros and cons. For example, SPS has complex control integration capability, and AFT Impulse has unique Chekhov simulation components. It is important to note that multi-phase simulator often not solving the wave equation with inertia term. Plus, with much increased computational cost and setup complexity, hence they generally are used for flow insurance study rather than serving sole surge analysis purpose. The first crucial step in detailed surge simulation is accurately defining the fluid model. For single-phase fluid, we need to specify properties like density, viscosity, vapor pressure, bulk modulus. Remember that these properties can vary with pressure and temperature. In certain cases, gas entrainment within liquid pipe can be approximated with a single-phase model, assuming gas bubbles are homogeneously distributed. Please refer to the graphs on the right as an example. As the gas volume fraction increases, the wave speed decreases significantly, and the relationship is clearly presented here. For multi-phase fluid like oil and gas mixtures, specialized fluid models are required, including black oil model or compositional-based models. Please note that when setting up the fluid model, consideration should include temperature dependence. If the fluid temperature varies significantly along the pipeline, using temperature-dependent properties needs to be considered, and also heat transfer. For pipeline exposed to varying ambient temperatures, incorporating heat transfer model can improve simulation accuracy. However, the surge events are often related to shock wave propagating. The time scale of wave is much faster than the speed of heat transfer. So an isothermal model is good enough under most cases for surge analysis, as long as worst case is simulated. So one common scenario we simulate is a pump trip. This could be a sudden power outage that shut down all pumps, or a partial trip when only some pumps are affected, including normal shutdown or planned trip, including seeking the verification of operating sequence, and also accidental unplanned shutdown, for example, due to a power failure. When the pump trips, the pressure in the pipeline drops rapidly. This negative pressure wave travels downstream, potentially causing cavitation and column separation. As the wave reflects off downstream boundaries, it can return as a positive pressure wave, leading to the overpressure when the cavity collapses. As we can see from the left graph, following a pump trip event, the initial hydraulic gradient line will start to drop, reaching the minimal hydraulic gradient line, then bounce back as the positive surge pressure up to the maximum hydraulic gradient line, and finally reaches equilibrium status to the final gradient line. Column separation and cavitation is a phenomenon that can occur during a surge event. If the pressure in a pipe drops rapidly to the vapor pressure of the liquid will vaporize, and a bubble of vapor will form in the pipeline. This is most likely to occur at specific locations, such as a closed end, the high point of all changing pipe slopes. When the pressure later increases above the vapor pressure of the liquid, the vapor in the bubble returns to a liquid state, which leaves a vacuum in the space formerly occupied by the vapor. The liquid either side of the vacuum is then accelerated into this space by the pressure difference. The collision of the two columns of liquid will result in cavity collapse that cause a large and nearly instantaneous rise in pressure. And this pressure rise can damage hydraulic machinery, individual pipes, and supporting structures. Many repetitions of cavity formation and collapse may also occur in a single water hammer event. And I will further illustrate this in a simulation example later on. Another important scenario is a pump start, which can also generate a positive pressure wave that travels downstream, potentially cause overpressure in the pipeline, especially when cavitation already occurs during startup. This simulation is also required when seeking operational sequence and maximum electrical power load. To accurately simulating the pump behavior during transient events, we need to establish a proper pump model. This model typically requires the following data, such as the pump curves and pump type, whether it's a rotordynamic or positive displacement pump, the pump and motor inertia, the pump check valve, the pump startup curves, or four quadrants pump curves if the pump operates negative flow or negative head conditions. The typical valve operations, as mentioned previously by Thomas, including rapid valve closure, such as an inline valve closure, control valve trip, an ESD valve trip, and rapid valve opening, such as a dilute valve and a sprinkle opening in a firewater system, control valve failure open. And similarly, the hydraulic gradient line changes can be summarized in the following figures. And I won't go too much details on this. To mitigate the risk associated with valve operation, it is crucial to use simulation tools and identify the appropriate mitigation measures. Key factors to consider when simulating valve behavior including valve types, whether it's a gate valve, global valve, ball valve, butterfly valve, and valve CV curve that associate with each valve type, and valve closure time. A rapid closure can lead to a more intense pressure surge compared to a gradual closure, and extending the valve closure time or a staged closure is a common design practice to mitigate the surge pressure. However, it is understood that the fast closure rate could be a must-have in some situations. Surge mitigation. So once we've identified potential surge issues through simulation, it is crucial to implement effective mitigation strategies. The graphs on the right show typical water transport system on the top and a typical oil transport pipeline to the bottom, with typical surge mitigation method shown with their common locations. You may find surge shaft, air vessel, feed tanks, and dual-acting air valves in a typical water transport system, and relief valves with relief tank or drum in a typical crude oil transport pipeline. Typical mitigations include change of pipeline itself, careful pipeline routing to avoid complex terrain, or use a stronger pipe, typical for hydroelectric plant when the turbine inlet valves and guide vanes are shut rapidly, or changing of pipe by using a less rigid material such as use of a plastic pipe rather than a steel pipe. Then change of valve closure arrangement, including closure time, pattern, valve type, for example, as mentioned before. Increasing the inertia of pumps and motors by installing flywheels to the pump. By doing so, we can extend the pump's rundown time, allowing the system to gradually decelerate and reducing the severity of the pressure wave. Surge tank and vessels. These vessels absorb pressure fluctuation by storing and releasing fluid. Air valves admit air to prevent vacuum conditions and mitigate pressure surge. The bypass line can divert flow to reduce the pressure surge during transient events, and we need to select the appropriate check valve to avoid check valve slam. Relief valves can be used to relieve excess pressure to a storage or drum, then pumped back to the system or removed separately. The last but not least, having well-defined operating procedures can help mitigate the consequences of unexpected events. In the next few slides, I'll share some detailed simulation model examples with surge mitigation recommended accordingly. I will make a start with a very simple water rising main example. The line size 4-inch with elevation difference of 58 meters and has a design flow rate of 113 cubic meter per hour with a length of 300 meters. The pipeline roll profile is assumed to be a straight line. The surge event simulating here is water transport pump unplanted shutdown due to a power outage. The two graphs shown to the top right indicate the pump discharge pressure trend against time, with and without surge accumulator installed at the pump discharge. As we can see here, pressure fluctuation is much severe without the accumulator. The addition of this surge accumulator helps to dampen the pressure fluctuation as well as lift the minimal pressure during a pump trip. A more clear view can be found below, with the pressure profile along the pipeline shown here with and without surge accumulator. At the time zero, the steady-state pressure profile are identical for the two cases. As the pumps start to trip, the pressure begins to decrease along the pipe, and the oscillation can be observed here. The red line with the surge accumulator exhibit a steadier behavior and a much higher minimal pressure reached. Hence, this simple example illustrates the benefit of surge accumulator, which is a very common device used to mitigate fluid transit, particularly during pump trip, to protect against the low pressure and column separation. When a pump trips, the accumulator acts as an energy source, releasing stored fluid to maintain flow and prevent excessive pressure fluctuations. This controlled release of liquid also helps to smooth out the transient event, reducing the risk of damaging to the pipeline and equipment. In general, surge accumulators should be placed as close to the pressure source as possible at the upstream end of the pipeline to effectively mitigating pump trip events. The size of the accumulator is crucial and depending on various factors, for example, including pipeline length, cross-sectional area, initial flow rate, pipe profile, and vessel type. For example, whether it's a conventional with air compressor or some design with internal bladder, or even with a dipping tube. The accumulator can be horizontally or vertically fitted, and its connection to the pipe also can be single or dual lines with some level of throttling on the return flow to further help dampen the pressure fluctuations. And its application is very common in water industry, but it can also be seen in the energy sector. The second model example is similar to the previous one, also a 300-meter water rising man to the same elevation. There is a high point at 250 meters before reaching the receiving reservoir, which is the potential location for air valve I choose as the surge mitigation in this case. And please note that surge accumulator is also a valid solution. And what I show here is an alternative surge mitigation by using air valve. The top two graphs shows the pressure trend and cavity volumes at pipeline high points against time. The top graph indicates the pressure trend at high points with and without air valve activated. With air valve present, for example, the blue line, the pressure fluctuation is much stable, and the minimal pressure will be controlled close to atmospheric pressure at this point due to the quick admission of air. Without air valve, the red line shows the pressure can drop to vapor pressure, and the vapor cavity will be formed at this location at multiple times. The bottom animation shows the pressure profile along the pipeline with and without air valve at high points. It clearly indicates that with air valve installed, pipeline minimum pressure does not drop below atmospheric pressure, hence eliminating the potential risk of cavity formation and collapse. Air valves are essential component in most water pipeline systems and serving two primary purposes, for example, ventilation and surge suppression. For surge suppression purpose, use of vacuum breaker valve with rapid admitting air into the system to prevent excessive negative pressure and mitigate the formation of vapor cavities. And while using air relief valve to slowly release air to cushion the pressure wave and reduce the severity of the pressure surge are very common. Those two valve functions can be integrated into one valve body, namely double-acting air valve. The location and sizing of air valve are crucial for effectively surge control. Air admission valves should be installed at point where the pressure is likely to drop below atmospheric pressure, such as high points in the pipeline. And air relief valves should be located at point where air tends to accumulate. In water industry, for example, AWWA M51 guideline provide valuable information on the location and sizing of air valves. Now let's move on to the energy industry, where liquid lines with crude oil and white products are very common, which subject to surge risk. So what I presented here is a typical example of crude oil transfer pipeline between process facilities, where spec breaks between a 300-pound and 150-pound system are specified. The stabilized crude oil transfer from the tank farm at the left to the export facilities to the right, with a few kilometers of pipeline. The transient scenario simulated here is the valve closure at various locations, such as we have SDV closure at off-spec line, the EST and PV closure at downstream of the pipeline, and the filter SDV closure and downstream pump trip within the 150-pound section downstream of the pipeline, as well as looking into pump trips and restart at the tank farm. As mentioned previously, the hydrocarbon liquid lines cannot use air valves because the product cannot be exposed to the atmospheric. A common surge mitigation solution is using pressure relief valves, leading to a properly sized relief tank. The pressure trend to the right linked to the case without relief valve, where high pressure exceeding design limit is identified after a sudden closure of the downstream valves or trip of downstream pump. By specifying correctly sized relief valve, or usually a set of multiple relief valves, we are able to mitigate the surge pressure by quickly diverting the liquid to the relief tank. And this example shows a much reduced pressure peak at this location, compared with a much higher pressure peak without the relief valve. And relief valves have different types, such as a spring-loaded valve, a weighted valve, a membranous valve, or even can be a burst disc. And these devices automatically open when the pressure exceeds a predominated set point, releasing excessive fluid to a safe location, such as a surge tank or surge drum. Hence, the surge relief valve is a common mitigation method when transporting hydrocarbon fluid. The location, capacity, and set pressure of relief devices are crucial factors to consider. They should be strategically placed to effectively mitigate pressure surge and having sufficient capacity to handle the expected flow rate during a surge event, and be set at a appropriate pressure to balance the protection against overpressure, with the risk of unnecessary discharge or oversized tank. The bladder accumulator may also be considered for some situations if pump trip leading to the column separation is a potential issue in energy industries. And in this example, the bottom illustration shows a typical force calculation using computer software AFT impulse. The transient force is composed of fluid momentum changes, the force due to pressure changes, and forces due to friction and other losses. Predicting these factors can be complex, especially during transient event when cavitation and column separation can occur. The graph on the right-hand side shows a typical force diagram between the defined elbows following a valve closure scenario. So one of the typical outcomes for surge analysis is determining the trend in forces acting on a piping system or pipeline between elbows. And these results from hydraulic transient simulation can be further used for stress analysis and export to other softwares for more in-depth analysis to check the pipe support design, for example. And in the next two slides, I will also show two more surge analysis examples. However, I won't go much in detail due to the time constraints here. This example is in energy industry. Loading and offloading terminals are also subject to surge risk. The surge event simulating here are pump trip and various ESD valve closure, as well as a brake valve decoupling within the floating hoses. And this is the offshore loading and offloading facilities using onshore and offshore pipeline by a single point mooring. And another example shown here is a firewater ringman within a large facility. And in this example, a range of valve opening closure case along with the pump start or trip are analyzed. Finally, let's summarize today's presentation with some useful takeaways. Hydraulic surge or transient pressure is a damaging phenomenon that needs to be correctly identified, evaluated, and mitigated. It is often recommended to conduct surge evaluation as early as possible. The surge screening based on Joukowsky equation is a quick and effective way of evaluating large quantity of liquid process piping. Under many circumstances, surge screening has its own limitation, and detailed software-based surge analysis is required, especially for pipeline and complex process system. Different surge mitigations needs to be considered to suit for different applications on the various industry sectors. And finally, remember that Fluor has SMEs across different global execution centers and abundant experience on surge design, vendor engaging, and procurement. I will now hand over to David for the Q&A section.
Right. Thank you very much to Thomas, Liang, and Niels. I see we do have a few questions remaining or a few minutes rather remaining before the top of the hour, which should allow us to get to a few questions here. And to those attendees, please make use of the Q&A tab to certainly ask any questions which should be addressed to all panelists. So the first one here, Liang, I'm going to send over to you to get us kicked off. And the question is this: are IFC isometrics required for the detailed simulation of surge? So over to you, Liang.
Okay, thank you, David. In general, yes, in a typical process facility. So having detailed isometric improves the accuracy of hydraulic simulation, especially when considered cavitation and column separation at high points, pipe racks, and so on. And by having the proper defined isometrics helps to create the simulations model, especially for a complex process plant, when additional requirement simulating the hydraulic transit forces between elbows. So that's why sometimes an initial surge study can be performed at early project phase based on estimated or assumed data to support a project cost estimate. Then we can recheck and confirm the surge mitigations during later stages when the information become available. So yes.
All right, that's great, Liang. And I think that's a good segue into another question that we received from the audience, and it relates to surge screening. And I'm going to ask Thomas to answer this one. Is there a recommended minimum line length and or size for which surge or screening analysis should be performed? So Thomas, I'll allow you to provide a response to that.
Yeah, thanks for the question, Dave. This is quite a nice question to illustrate, let's say, the practical implications of surge screening. The line length doesn't affect the maximally achievable surge pressure, or rather the Joukowsky calculated surge pressure. And you'll also not see a length-related factor in this equation. But in short lines and in normal operation, conditions don't really change fast enough to create the Joukowsky head, which creates this misappropriation as to where the surge can happen. If we put numbers to it, the speed of sound in water is approximately 1,000 meters per second, and control valves usually close at around an inch per second. Therefore, in a 4-inch line, we could reach the Joukowsky pressure only due to valve closure, only in lines longer than 2,000 meters. But I'll stress again that all lines can reach the Joukowsky pressure, and I think that's a nice loop back to Niels' safety topic, where in fact it did for, I assume, lines shorter than valve closure determined time.
All right, I think we can squeeze one, maybe two more questions in here. The next question is for you, Thomas, and it relates to one of the comments you had on slide number 20, where you commented to a 33% overpressure. And the question is this 33% exceedance over the maximum operating pressure or the design pressure?
That is over the design pressure.
All right, excellent. And I think just one last one we can squeeze in. And this one here is for Liang. And the question is this: can we identify a specific point in a network where the vacuum will occur? And the second part is, can we also calculate how much air needs to be sucked in to avoid pipeline collapse? So Liang, I'll leave you address that one.
Yeah, theoretically, yes. However, in a complex network system, it is very difficult. For example, even if you have a high point at one side, it's not always the worst case because you have to consider what is the remote distance with the largest flow rate occurs. So where the worst case can happen at other locations, not necessarily at the point you chosen. And your second question is relating to vacuum conditions. That vacuum is very tricky questions. And I don't think for any of the available commercialized software can accurately predict those. We have some models available across different softwares, but I have to say none of them can produce because vacuum and the column separation is a three-dimensional phenomenon rather than two-dimensional. And we need to carefully analyze and adjust those parameters based on engineering experiences. Thank you very much.
All right. Well, thank you very much, Liang. It certainly looks like that's all the time we have for questions today. And again, I would like to thank Thomas, Liang, and Niels for what I'd call a very informative webinar, and certainly the time you've spent with us today, as well as the time dedicated to preparation. I'd like to thank you to our audience as well for attending today. It certainly has been a pleasure being your moderator. We'll ask you to stay informed, certainly, of these events by visiting the Innovation Builders page on Fluor.com or following our social media channels using hashtag Innovation Builders. If you'd like us to send you email notifications for future webinars, please email us at innovation.builders@fluor.com with opt-in in the subject line. Finally, we appreciate your attention and certainly thank you again for dialing in today. We will send out a compiled list of the Q&A shortly, along with a notification that the webinar recording is available for replay on Fluor.com. If you have any questions or require additional information, please email innovationbuilders@fluor.com and someone from our team will get back to you. From all of us at the Innovation Builders team, have a safe day. Thank you.